Vehicles utilize air conditioners and heaters to cool and heat the interior in order to maintain a comfortable climate inside a car. Behind the dashboard, air ducts and the heater housing are located. The housing contains a heater core and a radiator that provides cold air, known as the air conditioning evaporator. The heater core heats the air that enters the passenger compartment. The air conditioning evaporator cools down and dehumidifies the inlet air. Additionally, the air is partially cleaned of small particles. Unlike the heater core, which is standard on all cars, the air conditioner is an optional equipment that may be missing in some models. The air conditioning system operates separately from the heater. To function, it requires an air conditioner compressor that is powered by the engine through a serpentine belt. Sometimes, a separate air conditioner belt may be used. Let's review the design and operation of a basic car air conditioning system. Its major components include the air conditioning compressor, the condenser, the receiver dryer, the evaporator, the expansion valve, 1 or 2 pressure sensors, 2 service valves, and the connecting tubing. And one of the main roles is assigned to the substance used in the system, the refrigerant. The key property of refrigerants is a low boiling point, for example, around -15 degrees Fahrenheit. These illustrations show that refrigerant boils even at 5 degrees Fahrenheit. The better the heat is supplied, the faster the process occurs, as heat is required for boiling. But let's include pressure as an additional factor. This graph shows the relationship between refrigerant state, temperature, and pressure. It is clear under which conditions the refrigerant is liquid or gaseous. Our samples are at atmospheric pressure and will eventually become completely gaseous. Placing samples in pressure chambers such as 150 psi increases the boiling point of the refrigerant. Boiling continues only in the third scenario, despite no temperature changes. These physical properties are used in the air conditioner's operation cycle, as the refrigerant transitions from gas to liquid and back to gas, effectively absorbing heat from the environment. Let us note that refrigerants are often referred to as freon, which is not always accurate. Freons are only a subset of refrigerants with a specific chemical composition, or those released under the registered trademark Freon. Let's go over the complete cycle of operation, taking note of the refrigerant state in the system and using average figures. The cycle begins with a compressor. The compressor doesn't run continuously. Rather, it turns on when the air conditioner is turned on. In the frequently encountered setup, engagement and disengagement are achieved through a pulley with an electromagnetic clutch. When the engine is operating, the clutch pulley revolves continuously. The clutch pressure plate, however, begins to rotate with the compressor only once the electromagnetic clutch is engaged. Let's turn on the air conditioner. The electric current flows into the coil stator located behind the pulley. The generated magnetic field attracts the pressure plate to the pulley, connecting them. The compressor starts. The compressor forces the refrigerant to circulate in the system and also compresses the gaseous refrigerant, raising the pressure from 45 to 220 psi. As a result of the compression, its temperature increases to 175 degrees Fahrenheit. The graph indicates that the refrigerant is gaseous under these conditions. Now, it's easier for us to turn the refrigerant into a liquid by releasing heat into the surrounding air. You will find more 3D video lessons in our Car Anatomy online course. Next, the gaseous refrigerant is then sent to the condenser located in the front of the vehicle, in front of the cooling system's radiator. The condenser is a type of radiator with multiple tubes and cooling fins, but its purpose is to condense the refrigerant. You can see one potential layout for the condenser's interior, in which the flow is split into multiple tubes going in the same direction, and each tube is further divided into multiple flows. This maximizes the heat transmission area. To improve visibility, let us simplify the design to a single serpentine tube. The condenser cools the refrigerant to 120 degrees Fahrenheit, causing it to condense, that is, transit from gas to liquid. The graph makes this quite evident. The temperature falls into the liquid state zone. At this point, the refrigerant cools, releasing the heat absorbed from the air entering the automobile, but we'll get into that later. Additionally, when the air conditioner turns on, the cooling system's fans turn on as well, enhancing refrigerant cooling. The next device in the path of the liquid refrigerant is the receiver dryer. In modern systems, a device resembling the receiver dryer is installed in the condenser and may be referred to as a modulator. This device collects and holds the refrigerant in liquid form, allowing for a smoother and more homogeneous outflow. Another task is to dehydrate the refrigerant. This is done by an absorbent material that absorbs moisture that has entered the system. Additionally, the refrigerant is cleaned of dirt and wear debris. Various types of filters are used for this purpose. The next component in the system is a service valve. Actually, there are two service valves, one on the high-pressure side and another on the low-pressure side. But we will return to them later. Next comes a pressure sensor, protecting the system from both overpressure and underpressure. The refrigerant then enters another device known as the expansion valve. It is located in the passenger compartment or on the partition between the passenger and engine compartments, adjacent to the evaporator. Let's take a closer look. Inside, there is a valve through which the liquid refrigerant is sprayed into the adjacent chamber. Due to the small cross-sectional area, there is a pressure drop from 220 to 45 psi. At this pressure, the refrigerant boils and changes from liquid to gaseous state. The refrigerant temperature rapidly lowers to its boiling point at this pressure. The process of refrigerant boiling occurs during its passage through the evaporator. Let's streamline the refrigerant path once more for better visibility. Boiling, or the rapid shift from a liquid to a gaseous state, is accompanied by the absorption of heat from the environment, as the conversion of liquid to gas requires heat. In this situation, heat absorption occurs from the evaporator and the surrounding air. So all we have to do now is direct the airflow through the evaporator into the vehicle's interior to reduce the air temperature. The heater fan generates airflow, and the air ducts direct it in the desired directions. When the refrigerant passes through the evaporator, it entirely changes to a gas. At the outlet, the gas passes through the same expansion valve, which helps maintain a consistent temperature in the evaporator by regulating the flow of refrigerant. The valve is adjusted by three forces: the adjustment springs pressure, gas pressure in the evaporator, and gas pressure in an independent chamber separated by a diaphragm. The spring pressure is factory adjusted, and the gas pressure behind the diaphragm plays a key role. If the temperature of the outgoing refrigerant rises, so will the temperature of the gas in the detached chamber, causing thermal expansion, and as a result, pressure on the valve via the diaphragm. The valve will open somewhat more, resulting in more refrigerant being injected, which lowers the temperature of the refrigerant in the evaporator and the temperature of the outflow. A cooler stream cools the gas behind the diaphragm, causing thermal compression and subsequent valve closure. As a result, the refrigerant injection rate reduces while the outflow temperature rises again. The valve, therefore, is constantly balancing to maintain a specific temperature at the evaporator output, which is determined during the expansion valve's production. The low-temperature, low-pressure gaseous refrigerant enters the compressor again, and the cycle is then repeated. The AC system has two sides: high pressure and low pressure. Low-pressure tubes are larger in diameter than high-pressure tubes. Each side features a service valve for air conditioner maintenance. One service valve is located on the high side and the other on the low side. Valve caps have markings that show which side the valve is located on. Let's note that for the long-term operation of compressors, lubrication of the moving parts is necessary. Thus, the system employs a special compressor oil, which flows throughout the system alongside the refrigerant, settling on and lubricating primarily compressor parts. We have examined a typical design of a modern automotive air conditioner. Let's take another look at the entire cycle, this time with a diagram. The compressor compresses the gas, raising both temperature and pressure. The condenser releases heat and converts the refrigerant into liquid. The receiver dryer filters and stores liquid refrigerant. The expansion valve generates a pressure differential due to its narrow opening area and regulates refrigerant supply to the evaporator. In the evaporator, the refrigerant returns to a gaseous state and absorbs heat from the environment. And a few remarks. In outdated designs, the expansion valve may have a somewhat different design, in which the refrigerant flow from the evaporator does not pass through the same expansion valve. Instead, a capillary tube with a sensing bulb is utilized to remotely record and communicate the temperature of the evaporator outflow to the chamber behind the diaphragm. The valve is then balanced in a similar manner to the prior design. The pressure sensor prevents the air conditioner from turning on when the pressure is too low to protect the system. It can also increase the fan speed if the pressure rises, and cut off the air conditioner if the pressure becomes critical. It is only one conceivable method for AC operation that makes use of pressure sensor data. Note that in other designs, additional sensors may be used, such as a refrigerant temperature sensor or another common sensor, an evaporator temperature sensor. The refrigerant temperature sensor data, together with other sensor readings, can aid in diagnosing a slow leak of refrigerant from the system. The evaporator temperature sensor keeps the evaporator from icing while the air conditioner is running. This requires some explanation. If the air temperature drops below freezing as it travels through the evaporator, the air conditioner will cut off to avoid the condensed moisture from icing on the evaporator. Condensation on the evaporator's surface and probable drainage under the automobile is a normal occurrence. In cold weather, at temperatures around the freezing point or lower, the activation of the air conditioner may be prevented, for example, based on the readings of the external temperature sensor, the evaporator temperature sensor, or another temperature sensor. This is important because in cold conditions, the refrigerant may not receive enough heat during the boiling stage to transition from liquid to gas. As a result, the boiling ceases, and liquid refrigerant can enter and harm the compressor. Next, let's note that compressors come in various types based on their internal design. We'll list the three main types: the already familiar piston compressors, scroll compressors, and rotary vane compressors. All designs are common and can have subtypes. Compressor pulleys are mostly equipped with an electromagnetic clutch, but there are also designs without an electromagnetic clutch where the compressor runs continuously. In this situation, the air conditioner is shut off by adjusting the compressor capacity. When the air conditioner is turned off, the compressor continues to operate with a low, near-zero load on the engine. For example, the air conditioner is now turned off. The compressor is still running, but the piston stroke is very low, and the compressor draws minimal power from the engine. When we switch on the air conditioner, the piston stroke is increased and adjusted to the desired performance. Note that such variable displacement compressor can also feature an electromagnetic clutch. Some compressors are electrically driven. However, such designs are uncommon and are typically found in hybrid and electric vehicles. As we wrap up the video, let's look at somewhat different, outdated air conditioning system design that used to employ an orifice tube instead of expansion valve. In these systems, refrigerant dosing is less precise. As a result, the accumulator, a device similar to the receiver dryer, is installed after the evaporator because the refrigerant is frequently found in a vapor-liquid state at the evaporator outlet. As you may recall, liquid refrigerant can damage the compressor. The liquid refrigerant settles in the lower half of the accumulator tank, while the gaseous refrigerant from the upper part enters the compressor. The lowest part of the suction tube has a small hole to catch compressor oil as it settles to the bottom. The pressure in the system is frequently monitored by two pressure sensors, one for high pressure and the other for low. Otherwise, this type of air conditioner operates in the same way. This brings our video about the vehicle's air conditioning system to an end.